All right, 12:30. Get started. Lord, thank you for bringing us together this afternoon. Thank you for everything that you do for us, Lord. I pray that you would help us to just continue on through the semester, make it through the last half unscathed. Help us to persevere and just get it all done. In your name we pray. Amen. All right. So today we're doing stuff and things, right? I've got too many mice. I've got too many computers. I don't know which one does what, so hopefully I can figure it out. Also, Zoom, just so you guys are aware, Zoom will be receiving an angry email and or maybe an actual letter from me demanding that that it can be used with actual software, not just Microsoft products. Because Simulink keeps crashing Zoom. So super fun. Super fun. Not so, it doesn't really affect you guys here in the room, but you know, those of you outside of the room, buckle up. It's gonna get bumpy later. Okay. So today we are gonna recap a little bit, do some things. Then we're gonna focus most of our time on the integrator block method for developing Simulink models. Okay. So it'd be really ideal and helpful if you guys had your laptops and were working along with Simulink, right, trying to get things going. The most confusing thing about last class was Simulink. Well, I'm assuming that that's going to be the most confusing thing about today's class as well. I know Simulink is new stuff. You guys haven't used Simulink at all in anything else before. It is a significant portion of your homework that's going to require you to check things using Simulink, right? So there's lots of practice that you get to use it. Today's class, we'll go through another way of doing it, right? All these methods are going to give you the equivalent model. However, there are caveats of when and why you want to use specific methods, right? We'll talk more about that later. Simulink in general, if you can draw the block diagram for your system, then you should have a pretty good idea of how to make the Simulink model for it. Now, I understand that there's different functionalities and different blocks and things, and those are things that are just going to come with practice, right? The things that are going to come with practice. Okay? If you do have any major specific issues with Simulink, right, please come to office hours, and I can help you run through some things. Keep trying to use the wrong mouse. It's starting already. You guys have any major issues or anything you want me to address right now before we start doing other stuff? No? Okay. These are the things that are due. The homework is now due. Well, I guess it's always been due on this date, but now it's closer. It's like 6 days away. If you haven't started the homework yet, I would highly recommend starting it sometime between now and Sunday. Those would be good times to start the homework. Ideally, you would start it like today, and ask questions if you need to. Lab, next week we'll talk more about the lab. Just so as a heads up, right, I made an announcement about homework 4, right, in Lab Cloud with some extra constants that, if you had tried some of those problems and you were like, I don't know what the capacitance of this tank is supposed to be, well, now you should know what the capacitance of that tank should be, because I gave you a number. But it's kind of hard to do an analysis without any numbers. I apologize. So now you should be good on those. Like I said, Lab 2, we'll talk about that more next week on Tuesday. Then homework 5, right? Next exam is going to be homework 4 and 5, right? Time domain responses and Laplace transforms. Those are the main thrusts of the exam. Okay. They will be asked in similar ways to the ways that the homework problems are posed, right? So anything that shows up on homework 4 and 5 is fair game, right? Also, right, we've gone over this before though, but you should still know how to make a model if you're asked to make a model. I know, big ask. How dare I ask you to remember something that we learned in the first 4 weeks of the semester, right? All that. We're good. Wrong mouse. Oh.
I actually do have a question about the homework before we kind of moved on, because you just mentioned the constant, sorry. For problem 12, do we need the laminar resistance?
Problem 12.
It's the fluid one in the tank. And when at least I modeled it, and I could be wrong easily, right? But I think we have to sub one of the Q's out for like delta P over RL, or is that not what we need to do?
Yeah, so you're going to want to make everything in terms of pressures, right?
Right,
that's
the
dynamic variable.
Okay, and then so when we do that, I think that RL comes into play because it's laminar flow.
Yep.
And we don't know the length of the pipe, so I can't really calculate RL.
Well, weren't you given a value for R1 and R2?
Oh, is that what it was? I thought that was like the radius of the thing. Okay.
No, that's the resistance.
Gotcha. Beautiful. Thank you.
Yep. Yeah. Okay. So, there, we can do this. So I told you guys that this was coming last class, end of last class. Sorry, so as a way of recapping what we did last class, right? We started off talking about approximate methods for modeling systems based off of system response, right? And we were given one that looked overdamped or like a first order response, right? And I showed you that we can take what we know from the plot and we can take that information and we can run it back to get an approximate first order model, right? And I said, we can also do this for second order systems. And look, here it is, right? So that being said, right? How would you be able to tell that you should be using a second order system to model this? There's two ways that you can from this slide. That's the first one, right? It tells you to use a second order equation, like literally right there, right? So you read the problem and you know what to do. The other one is what? How does this look? What kind of response do we have?
Yeah, sinusoidal plus reducing a magnitude of the time to stabilize.
Right. Right. So Taylor said we have a sinusoidal response that decays over time. And there's a special name for that type of response, right, that we talked about. Right? Is it overdamped, underdamped, or critically damped?
Underdamped.
Underdamped. Right? So that tells us something, right? We should be expecting to get a zeta of between 0 and 1 when we do this, right? And we've talked about second order underdamped systems, and we know that if we can get zeta and omega n, then we have all the fuel we need to get all of the other parameters, because all of our equations are in terms of zeta and omega n. So our focus here has to be finding zeta and omega n. Okay, so how do we do that? Well, first of all, we have this equation, right? mx double dot plus b x dot plus kx is equal to 10,000, not 1,000, but 10,000. 10 times 10 1,000s, right? 10,000 newtons. Great. We don't know m, b, or k. And that's typically how we're going to find zeta and omega n. So we need to figure out m, b, and k, right? Because here's the other half, the other side of this, right? We're asked to find the performance criteria of the system. But in reality, what you have here is, your competitor made a system and you want to know what makes it tick. Right? And rather than taking it apart and actually physically measuring all of the different components in there and then making this vastly complex model, we are going to test it to a step input of 10,000 newtons. And this is the response that we get at. And so we're going to try to estimate the mass, the damping, and the stiffness coefficients for this model as well. All right? Okay. Remember, if I want standard form, right? Standard form tells me that I have something like this, right? Where A times U of T, right? Where capital U is my step input. And how do I know this is a step input? It hasn't said it specifically, right? So how would I know to assume, or to know, how would I know that this is a step input? How would I know? What do I know about the input that is attached to this system? All right. So what do we know? What do we know about this number? It's big. No. What do we know about that number? Is it changing? Is it constant?
Constant.
Constant, right? What is a step input? Step input is a constant input that we're applying, right? Step looks like this. Well, I guess it never turns off really, right? It just keeps going. Remember, if we have a step, right, capital U of T is equal, for a unit step, it's equal to 1 from 0, well, for time greater than 0, right? That's what a unit step is. So a step is just some scaling of that, right? Just some scaling of that. Okay, so we know that this is a step input because it's given to us as a constant and we understand what that implies. All right. So how do we get that black equation into standard form, right? Well, we divide through by the mass. Right? Just divide through by the mass. Okay. But if you look at it the way that I've stacked it, I think it becomes pretty clear here, right? That K over M has to equal omega n squared. Right? B over M has to equal 2 zeta omega n. Right? Because we know what has to be in front of that coefficient. So where do we start? Right? We've got a lot of different things. Well, I don't know K and I don't know M. Right? So that seems problematic. But can I get any of these? Can I get any of these right now? Right, right off the bat. Could I? Sure. Let me ask you a question. What is special about steady state? What makes steady state steady state?
Constant.
It's constant. With respect to what?
The initial conditions, or no?
It
Time?
doesn't change with what? Time. There you go.
Ah,
Right? It's constant with respect to time. It doesn't change as a function of time. If it doesn't change as a function of time, my derivatives become 0. So at steady state, my equation, the black equation up here, becomes x steady state times k is equal to 1,000, or 10,000, sorry, times the unit step, which is 1 at steady state. So this is equal to this, right? Okay. So I can do this. And I can define x steady state from my plot, right? Because, ideally, you would have gotten a little bit more than that, right, on the tail end. But that's fine. We can come up with an estimate of what steady state is, right? So K should be equal to 10,000 divided by, and I'm going to say that x steady state is approximately 0.64 meters. I guessed, right? Well, it's better than I guessed because this plot actually has little markers. So I tried to take the average of where that line is, right? It didn't look quite like half of it. It looked like a little bit below, right? Again, as long as you don't tell me that it's 0.7 or like 0.3, right? Something that's outlandishly, clearly wrong, then, right? As long as you can make a reasonable case for whatever you picked, then we should be good. Okay. So it turns out this is going to equal 15,625 Newton per meter, which is really strong spring. But you got to remember that we're using 10,000 newtons of force, right? And it only moved 0.6 meters. So yeah. There's another couple of things that we can pull off of this graph that are going to help us immensely, right? A couple of things that are really easy for us to pull off. I can use this point and I can pull off the maximum, right? I can pull off the maximum peak value, which I will call X max, right? And I'm going to say X max is approximately 0.98 meters. And I'm going to pull off the time to peak. I'm going to say that's approximately not 1.5, but 0.15. 0.15 seconds. And there's a reason why you want to pick those two values off. First of all, they're easy to pick off. But second of all, if you look at the equations on the master sheet, the maximum overshoot equation is a function of zeta by itself. So if you can figure out what the maximum overshoot is, you can figure out what zeta is. And the other reason is, if you look at the time to peak, that's of an equation that's purely a function of zeta and omega n. So if you know Tp and you know zeta, then you can find omega n, and then the whole thing falls apart. And the whole thing falls apart. All right. Any questions so far? No? Nothing yet. All right. Bless. So let's start off with maximum overshoot. Okay. Remember what maximum overshoot is, right? We have two equations for maximum overshoot. Maximum overshoot is the absolute value of my maximum minus my steady state divided by steady state. I'm trying to determine the total amount beyond steady state that I've gone, right? I want to know what is the maximum overshoot that we have as a percentage, right? And so we can put this in, right? We said this was 0.98 minus 0.64 over 0.64, right? And that'll give us 0.531 or 53.1% overshoot. All right, so we've overshot steady state by about 50%, a little over 50%. There's another equation for maximum overshoot, though. The maximum overshoot is also equal to e to the negative zeta times pi divided by the square root of 1 minus zeta squared. And so now we want to solve this equation because I know the maximum overshoot and I can solve directly for zeta here, right? Well, you know, I'll take the natural log, both sides. I can plug in for the maximum overshoot. I know what pi is. I can solve this for zeta. And this is going to give me a zeta of 0.198. So, damped, underdamped, or critically damped, and why?
Is this underdamped because it's
Underdamped,
between 0 and 1?
Yes, 100%. It's underdamped because it's between 0 and 1.
Sorry, no.
Remember, 1 is the critical damping number, right? So anything under 1 is underdamped, and anything over 1 is overdamped, right? That's where the names come from. So we have zeta, right? I'm going to put a box around it because we know zeta is important, so we'll hold on to that one. But now we need omega n, right? And as I said earlier, we can use the peak time equation to get it. I know zeta. I know my time to peak. I can solve this directly for omega n, right? And if I do, I'll get 21.3 radians per second. Now we have everything that we need to get any other parameter that we are asked to find, right? But what we're going to focus on are getting the M, B, and K parameters first. We're going to try to get M, B, and K first. So remember, standard form. Let's go back and look at standard form. I know omega n. Omega n squared is equal to k over m, right? How are you either know that or you can look at the master sheet, right? Master sheet has some of these on there. Probably doesn't have that one. Yeah, no, it's right there. Omega n squared is equal to k over m. Like the second one down under, or the second one from the bottom of the page under system identification and time domain response. Omega n squared equals k over m. Just a heads up, there is a new master sheet version that I put on LabCloud, right? That I found some errors in some of the equations. So make sure you're using that one, not the old one. Okay. So we'll start here, right? I've got omega n squared is equal to k over m. Well, I know k, and I know omega n squared, right? So m has to be equal to omega, oh, I'm sorry, k over omega n squared. Which is equal to 15,625 divided by 21.3. So the mass is 0.03 kilograms. Sorry. Right, so that's super light, right? Do these units even?
Would 21.3 be squared?
Should be, yes. Thank you. So it's super small, but we're applying 10,000 newtons of force to it. I don't know what this is. It's Ant-Man, probably Ant-Man. Let's go with Ant-Man. But do these units even check, right? We should probably check units, right? So K is what? K is in Newton per meter. Omega n is radians per second, but it's squared, so it's radians squared per second squared, but it's also the inverse of that because it's 1 over that. So it's second squared per radian squared, right? But what's a Newton? It's a kilogram meter per second squared. Per meter, all right. Second squared. And radians is a throwaway unit, right? Radians isn't like a real unit. Right? Radians is units of 1, really, that we just repurposed to talk about angles. So comes out as kilograms. So good, we checked, right? Mass is good. So we'll save that one, right? Now that we know the mass, we can use this. B over m is equal to 2 zeta omega n. I know zeta, I know omega n, and I know the mass. So B is equal to 2 times the mass times zeta omega n. That comes out in Newton's second per meter. Or, right, if we wanted to get crazy, right, wasn't a Newton just a kilogram meter per second squared? Isn't this just really kilogram meter per second? Isn't this just a kilogram per second? Right? We'll just leave it at Newton's second per meter. Does this check? Well, we've got kilogram. 0.198 doesn't have units. Yeah. Kilogram. This is a kilogram per second. Right? We've proven that that's a kilogram per second. Right? So they're equivalent. So now I've got M, B, and K, right? So I can rewrite my model. I can say that this is 0.03x double dot plus 0.253x dot plus 15,625x is equal to 10,000. Right? So now I've got an approximate model, and I know that the system response from this model should look like what I just saw on my picture, right? The last part about this, right? We should talk about the settling time, right? Because that's a pretty key characteristic for our model. So settling time, right? Well, that's 4 time constants, right? But we know that time constant is 1 over zeta omega n, which gives me 0.237, and settling time is 4 tau, which gives me 0.95 seconds. I'm going to put a box around the model here. We could find other stuff too, right? We could find all the other things too. This is, once we find zeta and omega n, this becomes a plug and chug thing, right? There is a homework problem, right, where you're going to have to do this. There is a homework problem where you're going to have to do this.
Dr. D, I had a question about where you got your M value from. It was 10,000 divided by 21.3 squared. How does that equal 0.03?
One second.
It equals that if it's 15 point, but not 15,000.
All right, well, math error. It's going to throw all the other stuff off. Okay. Good catch. Let's fix that. Makes more sense anyway. 22.0. It's actually just 22 kilograms. All right. Let's rerun these. Oh, no. My bad, guys. I must have run this problem with weird numbers for some reason. Oh, well. Good catch. We caught it. The process is still the same. It just changes some of these things. Wait, is it? Hold on. Hold on, Noah. Hold on. Everybody, slow
It's
down.
34.4.
I was gonna say I got 34. But then you were so happy. I'm like, I don't know if I want to tell him.
Yeah, I used 10,000 instead of 15,000. That's
Oh Lord.
the problem. 34.4. 34.4 times 2 times 418 times 4. So it's going to be 290 for my damping. The rest of it stays the same. My bad. Okay. All right. Any other questions? Any other errors that I missed? No, not yet. Let me know. Again, right? You want to start by finding the steady state response, right? Why? Because we know what the steady state value is, right? We can read that readily off of our plot, and then we should be able to run it back. So, no other questions? Then we'll move on to this. The participation assignment that I left you guys with that hopefully people submitted prior to the start of class. I told you guys on Thursday that I wanted you to attempt to find the state space matrices for this, right, and turn it in prior to class. So, how do we find the state space? Well, we already did this once, right, with the transfer function. We found the transfer function for this, and that was good. But how do we? Wrong mouse again. How do we find the state space for this? Sorry, one sec. So I've got to get the state space matrices here, right? So I'm going to need two state variables, right? Why? Well, because it's the second order system. Right? I need two state variables. Which state variables should I pick? So the general rule of thumb when we're picking state variables is to pick the energy storage variable. Is there a wrong choice? No. You pick whatever you want, right? You just have to make it work, right? It's easy to pick energy storage because we already understand how that's going to affect, or we already have equations for energy, right? We understand that. In this case, we have a spring and we have a mass, right? So their spring stores energy by way of position, and our mass will store energy based off of kinetic energy by way of velocity. Right? So if we're talking about this in terms of state variables, right? I need x1 and x2. And I'll set this as y and y dot. So then x dot 1 is y dot, and x dot 2 is y double dot. Okay. Remember what we're trying to do with state space, right? I'm trying to create n first order differential equations for my state variables that are equal to some function of my state variables and my inputs. In this case, my input, we're just going to call that f of t. I'm not going to bother defining it as a step, ramp, or anything else. Why? Because it doesn't matter. It doesn't matter what it is. We are going to put it into Simulink, right? It doesn't matter if we're formulating this equation what it is. We just know that there's an input. I also need an output, right? So I'm going to assume that I want the position variable to be my output. Right, so I'm creating a single input, single output model. I didn't want to write y is equal to y is equal to x1. I think that that's confusing, so I just said y is equal to x1. Right? x1 is just the positional change of my solenoid. And I think that that makes sense for the output, right? And I think that if we were making the model of this, we would say that the input is the electromagnetic force, right, F of t, and the output is the positional change that we get of our solenoid. So remember what we're trying to build, right? We're trying to build these equations here, our state and our output equations. Right, our state and our output equations. Okay. So let's start with the state equation, right? Well, we know what x dot is, right? This vector x dot is just x dot 1 and x dot 2. X dot 1 is going to equal some matrix times my state vector, x1 and x2. In this case, I've only got one output, so I'm just going to call it u by itself. And some matrix times u. Sorry, x dot 1. What's my equation for x dot 1? Well, x dot 1, right, is this special case here. X dot 1 is equal to y dot, but y dot's equal to x2. So x dot 1 is equal to x2, right? How do I get that back out? It would look like that. All right, so if I use the top row there, I get 0 times x1 plus 1 times x2 plus 0 times u. So x dot 1 is equal to x2. What about my x dot 2 equation? Well, x dot 2 is that. Where did that come from? That came from me rearranging this equation. I solved this for y double dot. And then I substituted in my state variables and the values that I was given, right? And the values that I was given. That's where that. If we do this out, we get negative 175,000, negative 425 on this row. Then we can do our y equation, right? Our output equation. And we know that y is equal to x1. Row times column, 1 times x1 plus 0 times x2. There's no u in that equation, right? Remember, we're just using that equation here, right? That green box equation is what feeds us the output equation. A, B, C, and D. Why do we need A, B, C, and D? Because we're about to make a Simulink model using a state space block instead of a transfer function. And what the state space block wants is A, B, C, and D. That is what it wants. If you want it to work appropriately, you need to give it what it wants, much like, a toddler or Sheldon Cooper, which I mean is basically the same thing. Before we jump into the Simulink, does anybody have any questions about how I came up with the state space representation here?
I had a question. This is probably a simple answer though. The output state space equation, the C matrix, how did you know that was a 1x2 or a 2x1 instead of like a 2x2?
So you know that because we only have one y, right? Because remember what y is, right? Y is a singleton value, right? It's a singleton matrix. So you would have had to have a 2x2 if you had a 2x1 output vector. But you have a singleton output vector, so everything's going to be basically a single row.
Okay, cool.
Theoretically, if we were to be asked to measure it with a different variable, would we just change the x, or like how would we do that?
So instead, if we didn't want to use position, but we wanted to use velocity, is that what you're asking, Noah?
Yeah.
Right, so if your output was velocity, right, well, velocity is x2, right? So this would just change by becoming 0, 1, right? What if you wanted to measure the acceleration, right? Well, if y was equal to x dot 2, how would we do that? Well, check this out. Isn't x dot 2 just Isn't it just that? So you're just going to plug this in for that y matrix. Or essentially, you're using the bottom row of your state equation, right? So if you have other inputs or other outputs, right, the way that it changes everything is it's going to change that C matrix and possibly your D matrix, right? So if you're asked to find acceleration as a measurable output, then you really need to be looking, right, this equation right here, then also is your output equation, right? Okay. Any other questions? Yeah, no, I just saw your chat. The input is 12 Newton step function applied at 0.02 seconds.
On the exam, would we use Simulink and then like take a screenshot or something and put it on our exam?
No. So, Sean, good question. On the exam, you are barred from using MATLAB and Simulink. As much fun as it would be for me to read your guys' code and, and piece through it and make sure everybody's doing it correctly, I'd rather not. And so you're not going to have to do any MATLAB or Simulink on the exam. In the homework, if you're asked to do MATLAB and Simulink, I would very much take a screenshot of your output plots, right, and include those in your homework. That would be a very good idea. Answering the part of the problem that says check this with MATLAB or Simulink and just writing I checked this with Simulink and everything was okay might seem like a good idea, but it's not. You should prove that you checked it. Okay. Trust but verify. Okay. Trust but verify. All right. Any other questions? Yes, Jeremy. A screenshot for verification for the homework. Yeah. Just your output plots. I don't need to see like all of your code or anything like that. I'm going to go out and assume that if you were able to produce the appropriate output plot, that your code was correct. So what does this look like in Simulink, right? That's the one. Uh-oh. Hey, it shared, maybe? All right. So, hey, let's refresh our memories for a second. And we'll go over here. This is the one that we did in class on Thursday, right? This model on the left. And you can see we have our transfer function there, right? We have all manner of step inputs and other types of inputs that we can test and stuff, right? Remember, our step input is just 0.02 times the initial value, or 0.02 as my step time, 0 as my initial value, my final value is 12, right? That's all well and good. So what if you wanted to make this from scratch, right? What if you wanted to make this from scratch? How would you do it? Well, you could do the easy way, right? And copy this, right? Click it, Control-C, Control-V, right? And just put this right there, right? Like you could do that. And you see it says FEM1 there, which is exactly what I did when I made this. So I just copied and pasted it. Fine. It will copy over all of your filled in. It'll copy it in as filled in, right? So if you have a bunch of step inputs that are the same, then you can just copy and paste them. If you type state space into here, right? This will give you the state space blocks. Now, here's the thing. If you expand this, right, it doesn't ever give you anything interesting like the transfer function block, right? It will never give you a representation of what your A, B, C, and D matrices are, or if you do that, right? But what it will do is it will ask you for A, B, C, and D when you open it, right? So what's A? Well, we just found A. A was 0, 1, minus 175,000, minus 400. Right, remember in MATLAB, right, when you want to end a row in a vector or a matrix, right, you use the semicolon, so 0, 1, semicolon, tells it to go to the next row. Right? B is just 0, semicolon 25, C is 1, 0, and D is just 0. You can set initial conditions. We're going to set ours to 0. Well, this over here. We're going to set ours to 0. What's the other stuff that I have on here? And I've got an out to workspace, right? So I'm sending my Y for state space out to my workspace. And remember, what does to workspace do? Well, it takes this variable, What variable? Well, the variable that I name it, right? It's going to take the signal. I'm going to name the variable. I call it Y underscore SS for state space. I've set it to be an infinite number of data points and to have a decimation of 1, meaning 1 decimal place. Right? It's set up as an array, right? And I don't touch the other things. I do the same thing for time, except that this is coming to a clock, right? And look, right? Just to refresh our memories here. What happened? Whoa, there's too close. What happened here when we ran it, right? What did our response look like? First step. Right, it looked like this. Oh yeah, that's right. I have to share this screen. This is where I get into trouble. This is where things start to topple. Please hold while I crash Zoom. Right, so it looked like this. Right? Looked like that. Great. This is the transfer function. What would you guys expect the state space model to look like? What would you guys expect the state space model to look like? What do
A straight line.
we and stuff? What do you guys think? Does it make sense that the state space model for this system would look would look like this? Classy Zoom, classy. Kick me out of my own meeting. Would it make sense that this is what the response would look like? Is this what you would expect? Yes or no?
No,
No. Why?
well, I'm pretty sure we gave it some sort of input.
Sure. But how should it look compared to the other system? How should it look compared to the transfer function?
The same.
Should look the same, right? It's the same system. It's just represented different ways. So why does this one not look right? Well, look at the scale. The scale is off, right? So if we rescale it, we get the same exact model, which is what we should get because it's the same exact system, right? This is just different ways of not visualizing, but different ways of representing this mathematically, but we get to the same result, right? So what's nice about state space, right? The question that you asked in class on Thursday, Trevor, right? Why do we care? Why should we be using state space, right? What's the point if, what's the point? Well, this is the point right here, right? This box that says initial conditions that does not exist in the transfer function block. If I have a non-zero initial condition, I can throw it in here, right? So let's make it 0.05, see what happens. And I'll apply that, right? I'm gonna pull this up. I'm gonna share this with you guys again. All right, and look, I want to show you this too, right? You can run this directly from your scope window, right? And if I run this again, I'll get this, right? And I'll rescale it. Look, it starts at 0.05 meters. It starts at 0.05 meters, and then it drops, right? We started at some initial condition. We gave it an input, and it drove it back down to steady state because we started above steady state. Think about it this way, right? If the solenoid valve, instead of starting closed, started open, right, and you wanted to close it, this is what it would look like, right? Okay. So that's nice, right? That's nice that we can incorporate initial conditions. Why? Because not everything starts at zero all the time. Not everything starts at zero. You guys have any questions on that? Do we have any questions on that? No, we good? Because we're going to talk about this in a different way, right? So there's going to be three options available to us for making Simulink models, three different methodologies, right? The transfer function one is pretty straightforward, right? You make a transfer function, you give it an input, and out pops an output. State space is a little bit more involved. It's going to require us to do a full state space representation so we can find A, B, C, and D, right? But it is robust to non-zero initial conditions, right? The transfer function approach precludes us from entering any initial conditions because the way that a transfer function is defined, by definition, when developing a transfer function, you have to assume a zero initial condition. We'll talk about that more next week when we actually get into how to make Laplace transform transfer functions, and we get rid of this D operator and we start using the S operator, right? But more important than that, initial conditions aside, what if I don't care about the positional change of the solenoid? I want to know about the velocity. I don't care what the position looks like at the time. I want to know how the velocity changes with it. Well, I can't do that with the transfer function method, right? Directly. But what I can do is use an integrator block. The integrator block method is robust to non-zero initial conditions, right? Essentially, what we're going to do is we're going to take our acceleration for a second order system. We're going to take the integral of that to get the velocity, and we're going to take the integral of it again to get the position. Okay, that's what we're going to do. We can even use it for nonlinear systems. So if you have something that's nonlinear, this will work. Okay, so why is it? Why will that work? Well, what you're going to see is this is essentially the same as us setting up state variable equations, right? For the first part of going into state space without putting it into state space. So we're not going to define state variables, but we are going to solve our systems for the highest order differential that we have and try to create a block diagram that fulfills those criteria, right? So let's consider for a second our standard second order mechanical system, right? My double dot plus by dot plus ky is equal to f of t, right? Because this is a second order model, we would need two integrators, right? To get from acceleration to position, you need to integrate this twice. The first integrator integrates y double dot, the second one integrates y dot, right? We can set initial conditions in each of these blocks, right? You can specifically set your velocity and position initial conditions in these blocks, right? So, so there's that. So we're going to use the same, right? So basically all of these systems, right, we're using the same solenoid example. We're just using the mechanical portion of the solenoid. We've already come up with the system model, right? Here it is. 0.04 y double dot plus 16 y dot plus 7,000 y is equal to f of t. So we want to create this model in Simulink. And we already did do that twice. You're absolutely right. But this time we're going to use the integrator block method. All right, and I don't know why that happened, but that was awesome. I'm really happy that that decided to happen. All right. So let me share this. Yeah. Not that one, but this one. And I'm also going to get rid of this wire. That wire, that'll come back later. Don't worry, guys. Okay. All right. So let's do this. Let's do this whole dealie from scratch. And we're going to do this whole deal from scratch. So if I need to do this from scratch, how do I get this going? Sorry, give me one second. All right, so how do we do this from scratch, right? All right, so what I told you guys before, right? What are we looking to do here? Well, I've got 0.04 y double dot, and I'm gonna move everything else to the other side. Okay. Then I'm going to clear it and I'm going to divide. I'm going to divide this, right? Now look what has happened if I do this, right? If I do this, I have y double dot, and it is now a function of y dot and y, right? So I can draw a block diagram for this equation where I have y double dot coming out. So how do I do that? How do I do that? Okay. So let's rewrite the equation, right? Y double dot is equal to 1 over 0.04 times f of t minus 16 times y dot minus 7,000 times y. Well, first of all, I know my input, right? My input is f of t. What is it? Well, we were told that it's a step, right? A step function, right? That's fine. We'll define it more later. But for right now, we're graphically representing this. It's enough to know that f of t goes into something. What are we doing to f of t? Well, we're taking f of t, and we're taking f of t into a summing junction, right? And that's positive. And we're subtracting from that two values, represented by these lines. What are they? Well, f of t minus 16 y dot. Right? We'll say that this is 16 y dot. And we'll say that this is 7,000 y. Okay. What happens? What do we get out of this? What do we get out of this? Well, we're going to take this signal and we're going to multiply it by a gain of 1 over 0.04. And now this becomes y double dot, right? But where am I going to pull that y dot and that y from? Oh. We'll throw this through an integrator. What happens? Well, I get y dot out. Okay. I can pull that down here. If I throw it through another integrator, what happens? I get y out. And I'll siphon that off and send it through my other game. So I've created this double feedback loop here that defines y double dot, right? I want you to look at that equation at the top, right? Remember, homework problem 10. You're asked to find state variable equations, right? State variable equations are the first step in finding a state space equation. What is it? You solve this for the highest order derivative, and then you substitute in your state variable. We are just doing that, but not substituting in a state variable. Right? That is what we're doing. If you can do this, and you can draw the block diagram, now I've drawn that block diagram, I have everything that I need to go into Simulink and draw my block diagram in Simulink, right? Because it should look exactly like what we did here. You guys have any questions right now regarding this? Because what we're going to do is we're going to go into Simulink and we're going to build this from the ground up, okay? That's what we're going to do. So we're going to build this, right? Well, first of all, based on my drawing, I know that I need a step. I need a step input, right? Well, that's not really based on the drawing, but based on the problem we've been doing. We've been using this step input right? It asks for the step time up front. I remember that it's 0.02, right? But that doesn't matter because I still have to go in here anyway, right? Step time 0.02, initial value 0. Notice that it automatically gives you a unit step, right? Automatically gives you a unit step. We can set that up as such. Okay, so I've got my step input. What is my step input going into, right? Based on the drawing we just made, it's going to be going into a summing junction. So if you type sum, that first one for Simulink/math operations, we haven't really used the summing junction yet. I'm going to connect this to the summing junction, right? Because that's going to come in. Then I'm going to, but I only have one other input here, right? I have one other input. So how am I going to mess with that? Well, if I double click on my summing junction, you'll see you get the list of signs here, right? Well, I know I'm going to subtract two things from this, so I'll put in two negative signs. What happens if you got crazy with it and you just put a bunch of signs, right? This. You get a bunch of things that you can put in. We only need 3. We need plus, minus, minus. Plus, minus, minus gives us this, right? And that's nice looking and all, but I prefer to use the rectangle one. So I'll change it from round to rectangle, and I'll get this, and then I'll size it nicely, right? Make it look nice. What if you use circle instead of rectangle? Right? What happens then? What's clear it's wrong and you lose all the points, right? Oh, doesn't matter. Just aesthetically pleasing for me to have the rectangle. I don't like the circle. Do whatever you want. It's fine. It'll still work. Talking about results, man. Normally it doesn't scale so large. But anyway, what do we do now? Well, I don't know. I don't have my y or my y dot yet, right? So we're gonna leave this on. We're gonna move through it, right? So I'm gonna put my gain in. And I'm gonna type gain, hit enter, and I got a gain block. Now, if you don't click off of it, it'll have this little dialog box that comes up and asks you for the gain directly, right? 1/0.04, and I hit enter. And notice it says K on there. That clearly stands. It stands for Dr. K. Dr. K invented the gain block many years ago when he was a grad student. Not true. K is gain. Right? I made it a little bit bigger just so I could see what the gain actually is instead of just seeing K there. Right? That's what I did. Okay, so what's coming out of here? Right? What's coming out of here now is y double dot. So I need an integrator. Right? So we'll type integrator. Plop it in there. It'll ask for the initial condition. We're going to assume a 0 initial condition to start. We'll line it up. We'll attach it. Right? What does it look like on the inside? Right? You can set an external reset. Right? That's for if you're actually pulling in other data and you want to integrate other data. Right? You can set initial condition source as internal or external. You can set your initial condition. You can check any of these, right? We're just going to leave it as such, right? And so I'm going to label this. And I'm going to call this y_double dot. Because I'm super creative and I wanted a sweet descriptive name for this. I'm also going to make this a little bit longer so it doesn't. So that's y double dot. And what's going to come out of here is y dot, right? And y dot is going to go into another integrator. And if I could type it correctly, instead of integraster, then this would happen. I'll set a 0 initial condition again. Connect them. And I'll call this, I'll double click on this wire, and I'll call this y_dot. notice this, right? If I click on the wire and then I bring it over to one of these ports, it's going to want to automatically connect it. We shouldn't do that yet. What we're going to do is I'm going to put in a gain, right? I know that I have two gains. I've got a gain of 16 and a gain of 7,000, right? So let's put those on the playing field. Gain 16, gain, and 7,000. I'm going to increase the size a little bit. Okay, well that's awesome, but they're pointing the wrong way, right? Because right now, if I connect these things up, watch what happens, right? So y dot goes into here, and then this is going to come like over here, right? And that doesn't really, it's kind of messy, right? So what if I wanted to rotate that or flip that block, right? Well, I could do that. Control R will rotate it. You want to either right click, go to rotate and flip, and go to flip block, and turn it around, or press Control I. I mean, rotating it too, right, would be fine, but accomplish the same thing. And this one gets wired up, and I'm going to flip it. This one gets wired from here back up to here. But we don't have any way of checking what this looks like, right? So we're going to include a scope as well. So I'm going to throw a scope right on the end. And there we are. Okay. Before we run anything, I'm going to open my scope. I'm going to go to View, Layout, and I'm going to make this a 3-column. Okay, make this 3-column. Why would I want to do that? Well, whoa, that's not what I'm doing. Hold on. What I'm going to do is I'm going to move this up here. And yeah, I have the Y output, right? So I need to label this line as Y, right? So I'll label that as Y. I'm going to take the Y dot, I'm going to press Control, I'm going to click the wire, and I'm going to drag that up to my scope. I'm going to click on Y dot, press Control, click and drag this up to my scope as well. And now I've got three inputs into the one scope because I set it up in this way, right? I get 3 different plots, one for each, right? But what happens, let's just say we forgot to do that and we left it as 1. Okay? I'm going to run it. And I'm going to get this. And that isn't super helpful, right? But we can even do this, right? I can go into View, Legends, right? And they'll tell me, like, the yellow line is Y, the blue line is Y dot, the red line is Y double dot. And the reason that it does that, or that it knows to do that, is because I labeled the signals, right? Because I labeled those wires, now that's associated with them whenever we pull the signal somewhere. So this plot's not really super helpful, right? Because it doesn't really let us see all 3 responses at the same time. So again, go to View, Layout. We'll pick, notice what happens here, right? I can pick 3. I get 3 blue lights, right? That's telling me that I can have 3 plots. Anything else that's gray is going to be blank. So I'm going to pick these as columns, right? And that's great and all. I'll change the style So if you right click on the particular plot of interest and go to style, I can make this larger so that actually people, can see it, because I don't know why they decided to use the faintest yellow possible, but good for them, I guess, right? So look, I've got these things, right? These need to be rescaled. If you come up here, right, and hit the drop down, you've got three options. You've got scaling by the y-axis, scaling by the x-axis, or scaling both at the same time. I'm going to choose to scale the x and y limits together. And this is what we get. The top graph is my positional change. The bottom is the middle is velocity. The bottom is acceleration. Once again, right, the position is the same plot that we've been getting out the other two times that we did this model, right? By design, because we're trying to make sure that we're doing this correct. So integrator block, right? Integrator block. Great, we can get the same answer out, right? But let's see what happens. What if you know something about the initial conditions, right? What if we know something about the initial conditions? Let's go back in here. What if I have non-zero? What if my velocity initial condition at time is equal to 0? What if that's like, let's get crazy. We make it 100. What if it's 100? 100 what? I guess that would be meters per second. That's gonna be all right. And what if I know that my position is actually, 0.5? Okay. So I'm going to share the scope again. I'm going to run this from the scope. And if you run this from the scope with those initial conditions, changes the way that your output looks, as you would expect initial conditions to do so, because you have some energy already in the system, right? That's what the initial conditions are telling you. Okay. You cannot do this with the transfer function method. You also you can kind of do this, right? You can kind of do this with state space, except that you would need to define a C matrix to get out velocity and acceleration, right? So it adds to the amount of state space that you need to do. Where this really shines is if we wanted to start adding nonlinear components, because since state variable equations don't need to be linear, we can create block diagrams from nonlinear equations, which we'll talk about in a second. You guys have any other questions on this one? We tracking? Everybody doing all right? We doing okay? Yeah? Okay. Well, since everybody seems to be doing fine, I think that it would be a nice time for you guys to do this one. So let's take the next like 30-ish minutes, right? And I want you guys to work on this. I want you to create the model for the system using the first 4 steps, and then create the Simulink model using the integrator block approach, which is the one that we just did for this particular model. Okay? Mhm.
I missed how you changed the statement of the sum of the block.
Has there been any activity on the chat while I've been roaming? No. People at home.
You have any questions? No?
No. Okay. That's fine. We got a couple more minutes and then we're gonna review about it, okay? Couple more minutes. All right. Let's talk about it. But first, a word from our sponsors.
All right, guys, let's talk about it, okay? So what are we doing here? What are we doing? Is everything unfrozen? Good. So first thing we have to do is we have to make the model, right? That's the first thing that we have to do.
So if we're making the model, we should probably use the first 4 steps that we have. So what are we gonna do? Well, free body diagram, right? Hey, look, there's a free body diagram. My input is FA, my output is Z. Here's my truths. Right? FK is equal to KZ. Some of my forces is MZ double dot. FB is BZ dot. FA of T, right, is this piecewise function that I have going on. It kind of looks like a step, except that it starts at 8 and it goes to 0, right? Which is kind of like a reverse step, right? Kind of like a reverse step. We've been doing start at 0, pops up to a number. But there's no reason why you can't have a step that goes in the reverse direction, right? So we'll do our reduction, right? Minus FK minus FB plus FA of T equal to MZ double dot. We rearrange, right? Get all the inputs on one side, outputs on the other. Include our truths, right? MZ double dot plus BZ dot plus KZ equals FA of T. Then we'll solve for Z double dot. And when we solve for Z double dot, right, we're going to end up with something like this. Mine probably looks a little bit different than some of yours because I've essentially distributed the 1 over m, right, instead of leaving it as one term. Mathematically, it doesn't matter, right? It's just algebra. And you'll get the same result. Is everybody all right with this so far? Is everybody okay? Yeah. Does anybody have any questions on the model or drawing the block diagram? Okay. So once we have the block diagram, right, we can up and take that into Simulink. Let's do that. Let's go into Simulink. Look, here's a Simulink model. We have a Simulink model. Fantastic. Right, we know where all these things are coming from, right? I've got x dot dot, which is really z dot dot. Sorry, it is z dot dot. I just, for some reason, can't read that. Yes, you know, I probably need glasses. That's fine. Z dot dot, right? So what do we got going on, right? I've got my gains, right? I've got 5 over 2 and 200 over 2, right? That's k over m and b over m. Okay. Notice my input, right? I've got 2 inputs. I got 2 step functions. Why would you do that, Dr. D? Why? So here's the deal. There's 3 different ways that we can construct the input that we need, right? We need it to be, one second. Let's do it this way. I think this is a better way of showing it. Okay. Do this. I'm going to stop sharing for a sec. And I'm also going to okay. Yeah, right. All right, so imagine, if you will, for a second, we were using a step function, right? The way that we normally have been using a step function. And here's 8 newtons, right? And at time 0, I'm going to turn it on. And it's going to be on forever, right? It's going to be on forever. But that's not what our step function does, right? Our step function turns off at 0.05 seconds, right? Which we'll say, for the sake of scaling, is like right there, right? That's 0.05 seconds. Now, if I have a second step function that has a magnitude of negative 8 newtons here, that turns on at 0.05, I'll end up with a net gain of this green line, right? It'll just drop off and it'll be 0 for the rest of the time. So that's one way that we can do it. We can define a step function of 8 newtons that turns on at time 0, and one that of negative 8 newtons that turns off, or that turns on at time 0.05, right? And you add those two things together, and the superposition of those two signals gets us the step function that we want, right? The other way that we can do it is, instead of using a negative step function, we can superimpose a second step function of 8 newtons at 0.05 and subtract those two signals, right? Which is essentially the same practice that we just went through, right? So that's something we can do too. Or you can do it with one step function block, and you can set your initial condition, your initial step function value to 8. And you set your final value to 0, and you set your step time as 0.05. And that will do the same thing. Because all we're trying to do is make that. Right? That's all we're trying to do, is trying to make this step, essentially this pulse that is on when we start and off in 0.05 seconds. Okay? So, in order to do that, the way that I did it was I used, oh man, it's in a crash. I'm frozen. I don't feel frozen, but Zoom is telling me that I'm frozen. The bottom. Zoom is hilarious, guys. It totally kicked me out of this meeting. But I'm back. I'm back. Sorry. Let's try this one more time. Can everybody see that? Probably not. No? Okay, there we go. It was there for a second. Try it again. Okay. So there we are, right? We're good? Everybody can see it? No? Yeah? Yeah, hopefully. Okay. So look what we got, right? I did it the way where I used a step of 8 at 0 seconds, and I'm adding to that a step of -8 at 0.05 seconds, right? So the superposition of this signal, right, if I wanted to, I could put a scope right here, right, and I could take this wire and put it right there, right? And I could run this. And what we should see is the profile of the step function that we want. Hey, look, and there it is, right? And you can kind of see that. The time scale is 5 seconds, so it's difficult to see, but you know, I could always use my zoom tool and grab it and pull in, right? And look, it's at 8 until we get to 0.05, and then it turns off, right? Which is what we wanted. So you can always check, right? You can always check your signals and make sure they're doing what you want them to do. Yeah, well, that's great. But why don't we check out what's actually happening to this system, right? The top one is my position, the middle one's my velocity, the bottom one's my acceleration. So what do I have going on here, right? Well, I've got some second order damped sinusoid response for my position and my velocity, but notice my acceleration actually starts at a non-zero value, right? The other two start at 0. Right, well, that's because we put 0 initial conditions in for velocity and position, which is fine. But the acceleration starts at non-zero because we already have a force at the start, right? And force is equal to mass times acceleration. So we should expect to have some acceleration to begin with, right? Because we should be accelerating. All right. Do you guys have any questions on integrator block method? How we came to this particular this block diagram, this method? What was that?
Could you had for the input for both of the step functions?
Could I do what for both the step functions? No.
Show the what's inside the boxes, like the values.
Yeah. Let me see if screen share will let me have both of these on the screen at once. So these are my two step functions that I used. The other method, right, is to use a single step function where you would change final value to 0 and the initial value to 8. The other option. All right. Any other questions? Awesome. Okay. No other questions? Everybody's good? There are a couple of problems on the homework where you're going to have to think about how to superimpose your position, like your inputs, right? So just keep that in mind. There's a couple of them where you're going to have to create inputs that aren't readily available by a block diagram, right? So something like this allows us to make some unique inputs, right? Something like adding these and superimposing inputs on one another. All right, well, nobody's got any questions about that. Remember, the transfer function approach is the most concise approach, right? We find the transfer function, we have an input, we get an output, right? But it's not robust to non-zero initial conditions, right? So if you're told to use anything other than 0 initial conditions, you cannot use the transfer function method because by definition, the transfer function only exists when we have zero initial conditions. State space is still concise, but requires us to do a lot more legwork, right? We have to develop a full state space representation, right? It's flexible in that it allows us to set arbitrary initial conditions for all of our states, right? So we showed a single input, single output, right? What if we wanted to set multiple initial conditions, right? We had a huge system where we had multiple, like we wanted to set, voltages or, initial conditions for currents or voltages and mechanical properties. Well, you can, but you have to list them as, right? You have to list them as a vector of initial conditions based off of what your state variables are, right? So if x1 is I, and you want 5 amps initial current, right? Then that's the x1 entry, the first entry in your vector has to be 5, right? And so on all the way through all of your state variables. Okay? Finally, the integrator block method is likely the most flexible, as it allows you to set arbitrary initial conditions, but it also allows you to grab different signal paths, right? We can test velocity, position, and acceleration from it. It can aid us in troubleshooting in complex situations, right? Or make sure that our inputs all look the right way. Or it'll even allow us to account for non-linear equations. Alyssa's question is if there is a situation where the integrator block does not work. The integrator block is the most general way of doing this. So if you wanted to you could always use integrator block, right? You should always be able to use integrator block. There are certain times when it's overkill to do so, right? Because you're going to see a lot of systems, right? A lot of the systems that we use, we tend to assume zero initial conditions anyway, right? A good question. Right. So let's talk about nonlinear systems, right? We're going to talk a little bit about our nonlinear systems. So this is where the integrator block method really kind of shines, right? So let's consider a case where we have Coulomb friction, like dry friction, applied in our model, along with viscous friction, right? So we've got both viscous friction, so we have damping and we have Coulomb friction, right? So physically, what does that mean for our system? What does it mean if I have dry friction in my system? What would you expect? Yeah, Trevor.
Oh, is it going to change between like static friction and kinetic?
That's part of it, right? So what is so I guess, let me ask you this question then. What's the difference between static friction and kinetic friction?
One's like the friction before it starts moving, like that initial click off, and then afterwards it's kinetic.
Correct. Right.
So it's time.
One defines the amount of force that we absolutely need to actually start moving.
Yes.
Right? And the other one is we're already moving, right? And if you remember, right, friction kind of ramps up linearly. It hits static friction, then it dips down, and it's at kinetic friction the rest of the time. Now that's important because physically, this means that we need to overcome a certain amount of resistance initially in our system, right? So we need to overcome the dry friction, and the total friction of the system is the Coulomb friction plus the viscous friction, okay? So what if we use our previous spool valve model, but this time we want to see what happens if we include Coulomb friction, okay? So we're going to take our previous spool valve model, and we're going to see what happens if I take into account this nonlinear Coulomb friction. In order to do that, we need a model. Turns out this is the model, right? Rather than us deriving it. But spoiler alert, anyway, we've derived this model before, right? We like want to say like week 3 of class, right? We talked about nonlinearities a little bit, and we actually derived this model. So we've done it before. And we've got the signum function. Remember, the signum function is non-continuous. It returns the sign, right? If you have a negative y dot, it's going to return a -1. If it's a positive, it's going to return a +1. At 0, it's 0. Right? F dry is the magnitude of my friction force, right? So we need to know something about our parameters, right? And here they are. Here are our parameters, right? Well, hey, it's the same parameters that we've been using, right? These are the same parameters we've been using. Okay? We've been modeling this since Thursday. We've been doing this in Simulink since Thursday. We did it twice today, right? We did it one time on Thursday. We've been using this model ad nauseum. So let's try it one more time, right? So what do you guys think that the model will look like? What do you think that this model will end up looking like? I mean, we've done this model a few times. What do we think? What do we think? All right, so it's a nonlinearity, and Dr. G said that with a nonlinearity, we should use integrator block. Right? Okay. So should it look? All right. So let's find it. Let's find the model for this. Right? Now, hopefully, you guys were following along at home or in the classroom. You kept that old model that we did. Because what I would tell you to do, if you kept the old model, this one right here, and then we get back to business, right? Then we can. Oh, there's the crash. There's the Zoom. Zoom really does not like anything. All right, we'll try this. We'll try this again. All right, fantastic. So I'm talking about this model, right? This is the model that we made earlier. We did the integrator block for the spool valve, right? Where this step input represents our electromagnetic force. Okay, so this is what we did. What we want to do is we want to incorporate that extra term, right? So the model is the same, except that we have this extra term, F dry, times the signum function of y dot. Right? So how do we get the signum function involved here? Well, that's a great question. Turns out that if we kept that model the same, and if you kept that model, I would have said, if you kept that model, I would say copy it, paste it, throw it down to another part of your workspace, and alter it. Right? And how are we going to alter it? Well, we're going to turn this branch in here, right? Because what are we missing from this model? We're missing F dry times signum of y dot. Well, I'm going to take my y dot and I'm going to throw this into this block. What is this block? This block is called sign, S-I-G-N. Okay? So S-I-G-N, throw it in there. Right? Okay, cool. Well, what does sign do? Sign returns a 1 for a positive input, a -1 for a negative input, and a 0 for a 0 input. Right? That's what it does. And that's going to go into a gain block of 0.4. And that's going to come back up. We're going to add another port to our summing junction, right? We're going to add another negative sign, and we're going to subtract that from the whole. Okay? So what I'm going to do really quick is I'm going to come up here, and I'm going to grab my original one for Y, and I'm going to drag it down into this model right there. Okay? And I'm going to turn my time back to 0.1 seconds. And I'm going to run this. I forgot that I set initial conditions on this one. I gotta change that. So I'm gonna plot this. And we're gonna get this out. Now, it might be hard to see on the screen or at home, so let me try doing this. Is that better? Kind of. Kind of. There, that's probably a little bit better. Maybe. This is good. Okay. So we've got a couple lines here. The red line is my linear model, and the yellow line, which is now really hard to see, and the blue line is my nonlinear model. So my linear model overshoots the nonlinear model by a little bit and then comes back down. But steady state is basically the same for both, right? It's basically the same. We overshoot, instead of being at instead of being at 2 millimeters, right? Our nonlinear is at about 1.98 or so. So, okay, let's look at a better picture of this. All right, let's look at a better picture of this. I have a better one over here. Here it is, right? The black line, or the solid line, is the nonlinear, and the dashed line is the linear system. So in this case, for this system, our linearized model estimates fairly well the nonlinear, more accurate model, right? And it's nice, because we could use Simulink to model that without having to do anything else, right? And that's where the power of the integrator block method lies. Okay? In the fact that we can do things like that. So we can handle a nonlinear model. Turns out for this one, right, what happens if we get like a large disparity between our linear and our nonlinear model? Well, we have to go back to the drawing board with our linear model, or we have to commit to using the nonlinear model, because the nonlinear model is going to be more accurate, right? And for this small scale system, it's not a large amount of computational time, right? But if you start chaining this together with a nonlinear electrical model and then put that in an entire system of, networking multiple solenoids together, right, for flow and things, now you're talking about stacking your computational cost, right? You guys have any questions about how we can handle nonlinear models? We'll do another one on Thursday. Right? We'll go through another one kind of on Thursday. Before we go, I want to kind of introduce this. We'll tie up the Simulink stuff on Thursday, and we'll jump into Laplace transforms. Okay, that's the plan. So I think you guys you've started to see it maybe a little bit. Maybe you haven't. We haven't done anything overly complex, but we can create any system that we want to using these block diagrams, right? And the more system parts that we add, the more cluttered the workspace is going to get, right? Especially if things start tying into each other and you'll have wires everywhere, right? And so we can use a specific block, a subsystem block, to kind of clean up our models and keep things isolated as specific subsystems, right? So for example, right, if you had an electrical component and a mechanical component, you can keep those two things separate and then use the subsystem blocks to interface between the two, right? So there's a couple of ways, right? You can do it the first way here, which is to create a subsystem separately using Simulink and then use a bounding box. And that's a process that is covered in your textbook in Appendix C, but not one that we're going to cover in class, because the way that we're going to talk about it is by just using the subsystem block from the ports and subsystems library. Okay. So once again, right, we will be using this, but this time we're going to be adding our electrical component to it. So on Thursday, we'll start off doing this. Okay, we'll walk through this model, how to use subsystems. Then you guys will do one more Simulink problem in your groups, and then we'll jump into Laplace transforms. Okay? I think we're just gonna call it there for today. All right. Bean.